Hello dear student. In previous class I discussed about the valence bond theory, and here I discuss the limitations and of valence bond theory, and their limitations, mainly the valence bond theory actually says that in a summarized form, actually it says that the central metal ion, there is a central metal atom or a metal ion. It has a d orbital, and this d between the 5 d orbitals, there must be a vacant d present. And when ligands come to this metal ion, ligands having a lone electron pair or a negatively charged ion, that is the central metal ion must have a vacant d orbital, and the ligand must have a lone electron pair. When ligand comes to the central metal ion, the lone electron pair of the ligand donated to the central metal ion, and there is a bond formed. This bond is known as coordinate covalent bond, and the metal ions d orbital are somehow hybridized. That is their energy and the ligands coming to this electron pair coming from the ligand, this orbital and metals orbital having, there is a energy difference, and the energy of the d orbital is of the metal ion, central metal ion, and not only the d orbital, there is a s orbital, p orbital also present. And so there must be a hybridization, that is all the orbitals having the same energetic field, and so there is a hybridization, and this hybridization we can predict the shape of any type of complexes, and whether from this hybridization we can explain that whether it is octahedral or tetrahedral or square pyramidal or planar, etc. And there is a two type of complex formed. One is low spin complex and another is high spin complex. Low spin complex, generally we see that in the valence bond theory, when there is a strong field ligand, in spectrochemical series there are some ligands which are in the first position, they are weak field ligand, and at the last position these are strong field ligand. So strong field ligands generally form a low spin complex, and weak field ligand generally forms a high spin complex. So valence bond theory, from this valence bond theory we can explain many type of characteristic of this complex. The limitations of valence bond theories are mainly the color of the complex. There are so many complexes, coordinate complexes, which are colorless, which are having different type of colors. This cannot be explained from this valence bond theory. And there is another important limitation is magnetic behavior of oxygen. Actually, the O2 it acts as a dimagnetic according to valence bond theory, but it is found that oxygen is a paramagnetic, so magnetic behavior cannot be explained from this valence bond theory. And another is fractional bond order cannot be explained from this valence bond theory. There are so many compounds like the bond order is 2.5, this cannot be explained, and thermodynamic stability also cannot be explained. Coordination number, if the coordination number is 4 for any type of complexes, there are two type of complex must be formed. One is square planar, that is gsp2 hybridization, and the other is sp3 dsp2 hybridization square planar, and the other is square planar, and the other is sp3, which is tetrahedral. Which elements are, which compounds are tetrahedral and which are square planar, that is cannot be explained from this valence bond theory. Metal which forms inner complexes or outer complexes, that is which complexes has a p2 sp3, that is it is a inner d orbital complex involved, and whether it is sp3 d2, this cannot be explained properly from this valence bond theory. And so valence bond theory having some limitations, that is but it must calculate the magnetic moment, that is magnetic behavior can be explained, but in a proper manner it can be explained by crystal field theory. The magnetic moment actually in valence bond theory can be explained by number of unpaired electrons present, but in crystal field theory, the new explanation of the magnetic moment or magnetic behavior can be explained. It is by the splitting of d orbital of the central metal ion, and this crystal field theory means there is a one metal, whether it is metal atom or metal ion, and some ligands are coming to the central metal ion, and ligands coming to the central metal ion, whether it is along the axis xyz or between the axis, and the central metal ions d orbital, that is 5 d orbital here present. These d orbitals are different type of d orbitals present. D orbitals are generally, we see that dx square minus y square, dz square, dxy, dxz, and dyz. We see that in the central metals d orbital, the 5 d orbitals if there is no ligand present, that is in absence of ligand, the central metal ions d orbital are almost degenerate, that is all the d orbitals energy almost same, but in presence of ligands coming towards the along the axis or the between the axis, on this basis the d orbitals splits. D orbitals having dx, dyz, dxy and dxz, these 3 d orbitals are in a same category, and the dx square minus y square, dz square having another category. So here the lobes of the d orbital are along the axis, and these two, and these 3 the lobes of the d orbital between in between the two axes. When the when the ligands come to the central metal ion, in case of a octahedral system, when the ligands actually come to the central metal ion, the ligands lone electron pair and the metal atoms electrons are repelled to each other, and there is a electrostatic force of attraction between the central metal ions positively charged and ligands electron pair. So there is a bond formed. This bond is known as coordinate covalent bond. But there is also a repulsive force present, and this type of repulsive force splits the d orbital of the central metal ion. In case of octahedral system, the ligands come to the central metal ion along the axis, that is along the x, y or z axis. So the metal ions d orbital having lobes along the axis, that is dx square minus y square and dz square, are highly energetic, and the d orbitals between the axis, that is dxy, dxz and dyz, these 3 having lower in the energy state, and this d orbital of the central metal ion, 5 d orbital, that is in case of octahedral system. Here in case of octahedral system, the 3 d orbital of the central metal ion in presence of ligand, that is absence of ligand. Here the absence of ligand, and here the presence of ligand, means when the ligand comes, the d orbital, all the energy of the d orbital increases, and these d orbitals energy splits into 2. One is T2G and the other is EG, and this center is called, it is a standard, this center is called berry center. The energy gap between the T2G and EG, this T2G is 3 orbital, that is dxy, dxz and dyz, and that is dx square minus y square and dj square. Here it is dxy, dxz and dyz. So the energy difference between these two T2G and EG is called delta O for orbital system, or 10 dq. And each the orbital having energy lower than the very center is minus 0.4 delta O, or 4 dq, and the energy having greater from the very center, each orbital having energy plus 0.6 delta O, or 6 dq. Now we have to calculate different type of CFSE for different systems, D1, D2, D3, etc., and whether the complex is low orbital, low spin complex or high spin complex, and if the central metal ion attached to the ligand, whether the ligand is strong field ligand or weak field ligand. All these are shown in this picture. There is a picture between the valence bond theory and crystal field theory in case of FeCN whole 6 minus 3 and FeF6 minus 3. Let us represent there is something difference, we find out the differences. FeCN whole 6 minus 3 and FeF6 minus 3, in both the cases the central atom is Fe plus 3. Fe is in a configuration is 36 4s2, and Fe plus 3 is the outermost electron goes out and one electron from this D, that is 35, and 4 is 0. So it is a 3d5 system, that is in 3d 5 electrons are present, and the left is 4s and 4p orbital. In case of FeCN whole 6 minus 3, Cn minus is a strong field ligand. Due to strong field ligand presence, the d orbitals, d electrons are somehow paired, and if d electrons are paired, the number of d electron unpaired in condition is here only 1. In FeCN whole 6 minus 3, if the electron goes to here and this electron goes to here, the only one unpaired electron present, and so the magnetic moment is somehow less. Magnetic moment is equal to n into n plus 2 root over, that is number of unpaired electron is here 1, so root over 1 into 1 plus 2. And the 4p and 4s and 4p orbitals are vacant, so the hybridization must be d2sp3, that is there must be 6 Cn minus. It is necessary to fulfill there is a vacant 6 orbital is needed, so these 2 orbital are vacant, 1 orbital and here 3 orbital, so total orbital is 6, and this d2sp3, that is 1. And in case of weak field ligand, there is no pair, that is all the electrons are unpaired. And in case of CFT, from this theory it is to be noted that T2G and EG, this here also be Fe plus 3 means 3d5 system, and d5 in case of d5, and in case of CFT for Fe plus 3 system, that is a d5, and here Cn minus is a strong field ligand. Here the d orbitals is split into two, T2G and EG. This T2G having 3 orbitals and EG having 2 orbitals. Now the 5 electrons of the Fe plus 3 system, that is generally according to Bond's rule, electrons are occupied as their energy level increases, so 1, 2 and 3. The 4th electron coming to this, there is 2 options. One is the 4th electron goes to here or goes there. There is 2 options, the 4th electron 1, 2, 3, and the 4th number of electron goes to here or goes to there, which is in case of strong field ligand take place. Actually the strong field ligand, the delta O is maximum and pairing energy is minimum, that is to pair the energy, to pair the electrons, there is a energy required or energy necessary required, it is called pairing energy. The pairing energy is minimum and delta O is maximum, means the energy gap, as the energy gap is maximum, electron has no ability from T2G to EG goes there, that is the delta O or energy gap is maximum, and delta and P is pairing energy is minimum, means it occupies in the pair condition. So it is a better tendency for this electron, 4th electron, in case of strong field ligand goes to T2G, not in EG. So the 5th electron goes here, fifth electron goes here, that is the number of unpaired electrons here also be 1. In case of CFT there also be 1, and in case of CFT for the same complex FeCl whole 6 minus 3 number of unpaired electrons is 1. In case of here it is a low spin complex, that is number of unpaired electron is minimum, and it is a inert complex. In case of valence bond theory, you see that its hybridization is D2sp3, and in case of FeF6 minus 3, in both the same cases number of unpaired electron, number of magnetic that is magnetic moment value etc are same, but in case of there is some difference or some or the difference is some mechanism, that is there is only just inner d or outer d electron involved outer d orbital, and here is the splitting of the d orbital, that is whether it is greater than delta O greater than p or p greater than delta O. In case of FeF6 minus 3, the central atom also be Fe plus 3, that is D5 system. Here also 1 2 3 4 5, and the number of unpaired electron, number of D5 electrons are, that is 1 2 3, and the fourth electron goes here or goes there. There are two possibilities, but in case of midfield ligand, delta O is minimum, that is the energy difference is minimum, so the fourth electron occupies there, it is not possible, and this electron goes from here to there. If as the energy is, pairing energy is greater than the delta O, pairing energy greater means it is unstable for this fourth electron to paired condition, in a paired condition, so it goes from T to G to Eg and forms a stable and a stable complex, and which is high spin complex, and the fifth electron goes there. So all the electrons are unpaired, so the number of unpaired electrons is 5, so the magnetic moment also increases from the FeCl whole 6 minus 3 system, and its one system is, it is a outer d orbital, that is sp3 d2 hybridization involved there. And I here see that the CFAC value, how to calculate the CFAC value of a coordinate complexes, CFAC. Firstly, I represent you for a D5 system. Here I calculate for a D5 system the CFAC value. D5 system means here, D5 system means it is a strong field ligand or low spin, and in case of high spin, that is here d orbital, and this d orbital having T2G and Eg. D5 system low spin complex forms, that is the number of paired condition is maximum, so D5 system here 1 2 3 4 5, and 1 2 3 4 5, and there is no Eg is no electron, so T2G 5 Eg 0. In case of D5 system, in excited state, then d orbital electrons are paired, but in general form there is 5 unpaired electron. And in case of low spin complex, that is presence of any strong field ligand, then T2G5 Eg0, and the CFAC value is, for each T2G electron minus 0.4 delta O. Number of electron is here, number of electron is 5. Number of electron is 0, and each Eg number amount of CFAC plus 0.6 delta O. And here the pairing energy, that is here 2 pair. In case of D5 system, actually there is no pair, so 2 minus 0 into P. 2 minus 0, here 2 pair, there is no, that is here minus 2.0 delta O plus 2P. But in case of a D5 system with a high spin, that is 5 electron 1 2 3 4 5, and there is T2G 1 2 3, and Eg is 1 2. So here CFAC is equal to minus 0.4 delta O into number of electron is 3 plus 0.6 delta O into 2. Here there is no P present, there is no electron pair present. So you have to calculate for any type of system, whether D6, D7. In case of I represent U, in case of a D7 system, that is there is 1, 2, 3, 4, 5. T2G and EG, here 7 electron, that is in case of low spin complex there is a paired electron, so 2 to 4 and to 6 and 1 is 7. So here how to calculate the CFAC? Yes, CFAC is equal to 6 into minus 0.4 delta O plus here 1 into plus 0.6 delta O. Here number of electron is 3, pair of electron is 3, and here pair of electron is 2. So 3 minus 2 P. You have to calculate from this the CFAC, and in case of a high spin, that is a weak field ligand, you have to calculate the CFAC of a D7 system. That is 7 means there is 2, 4, 5, 6, 7 and T2G and EG 1, 2, 3, 4, 5 and here is 6, 7. So minus CFAC is equal to there is 5 T2G 5, EG 2. So 5 into minus 0.4 delta O plus 2 into plus 0.6 delta O plus here pairing energy is 2 paired and here is 2 paired, so 2 minus 2 into P, that is 0. Here the value is 0, and you have to calculate from this the CFAC of both the D7 system.